I give the floor now to the next speaker.
To the third and last final session of our seminar. My name is Bernhard Knoll. I'm Vice President of the Union of European Railway Engineers Associations, and I would like to give you first some additional information. I hope every one of you still has covered for the evening dinner his license or his business card you have received in the early beginning today when you received your badges. So I would like to, I would be happy if you could all join our dinner at 7:30 in the evening to exchange knowledge and experience with us after the meeting today. Please don't forget it. And the second announcement I want to give, there's a very beautiful journal. It's the Cargo Freight Journal. It is written in English and Bulgarian language. You will find it outside the door when you leave the session afterwards. There are, I hope, enough brochures for everyone. It's for free. You can take it with you. You will find information even on this seminar today already written in this booklet, in this journal. So feel free to take it with you and have a look at it. I think it's a very good information about freight cargo you can get. Next, I would like to introduce to you the first speaker of the session. It will be Marco Corradini. He's an expert in construction and maintenance of railway infrastructure. He works for the Swiss Federal Railways, as I have heard yesterday, and I give him the floor for his presentation on exchange of best practice as catalyst for interoperability. It's your floor. Thank you.
Thank you, Bernhard. I hope you are enjoying the conference. And as Bernhard said, I'm Marco Corradini. I work for the Swiss Federal Railways, but today I will be talking on behalf of CIFI, because I will do some considerations that go abroad of the technical content of what we have done by the Swiss Federal Railways. Just 2 words about me. I work in the south region of the infrastructure of the SPB. I'm the coordinator of different activity from track, overhead, civil works, and environment works, and I'm in this position over the last 3 years. And but I have, for many years, I worked on the Gotthard base tunnel and Ceneri base tunnel. I was also by Alp Transit in the build of these 2 big tunnels. And so, in my position as coordinator, it would given me this work to coordinate the future track renewal in the Gotthard base tunnel, and in the future in the Ceneri base tunnel. So, one step back. This is the content of what I will say. Just a little publicity about Switzerland. This is a picture on the Oberalp Pass. So if someone wants to enjoy railways, this is a good opportunity to see the wonderful landscape in the Alpine region. I will leave this presentation. So here you can read what are the themes that I will show you. I start with a jump back in the origin of the railways. The railways next year will be 200 years old. It's common to say that railways were born in September 1825 in England. So they are 200 years old. But in my presentation, I will go speaking about rails, and rails are even more older than the railways, because the first example of using rail was in the 15th century in many different coal mines in Europe. We say that the rails, as we know today, were born at the end of the 17th century with Aesop, and so they are, as I said, more than 200 years old. After Aesop, there was Charles Vignol, and we know that the rails that we use in Europe are called Vignol's rails. If we go further, we can remember that railways had a big growth as they were born, and here I want to mention that at the beginning of the 18th century, they built a lot of kilometers in Europe. They reached the length of about 200,000 kilometers in Europe, and every year were built about 300, 800 kilometers, so a huge amount of kilometers that today we can never think about. And this was the moment in which the railway had the big success in Europe. But after the 19th century, we start with the 20th century, and here the railways had, unfortunately, a big decline. This was due to the financial cost, because, as we know, infrastructure is very expensive, and in the railways, the different countries decided to find a way to give work to different workers. So the cost, infrastructure, and the personnel was very big. And in this situation, at the end of the 1960, 70, it was very difficult to go on, because road traffic was expanding overall in Europe, and the European community decided that railways had to be revitalized, because modal split should have changed in favor of rails. And in this direction, they have written a different amount of rules, of regulation. Here I've listed in this slides and in the next one what are, in my opinion, the most important ones. We start from the 1991, when the European Union decided to separate what is the infrastructure to what is the railway undertakings, and to liberalize the market in Europe. I will not go through all this regulation, because we are at the end of the day of today, and we have just mentioned all of these rules. I want only to mention that this was a decision that was taken in Europe, because if speaking with the American, they took another decision that the infrastructure has also to add the vehicle. So there are different ways to see how to implement the railways, and Europe has taken this one. So this I leave for your lecture. And now, after this short introduction, and to be concrete, what can we say after about 30 years of experience in the introducing of these rules to revitalize the railways? We can take figures of merits. They measure what we have reached after so long period. And if we look at freight transport in Europe and passenger transport in Europe, this data comes from the Eurostat. We take in consideration a period of this 30 years. We can see that from the end of the 90s till the beginning of 2020s, there was a change in the model split. This is freight transport, where road increased and rail decreased. And if you look at passenger transport, the situation was stable. If we make a comparison between passenger cars and what was the situation of passenger cars at the end of 90s and at the beginning of 2022. If you look at freight passenger transport in freight, there was a little increase, but about 0.2%. So very small. So what can we then summarize from this picture or from this data from the Eurostat? We can say that even though that the European Union tried to give impulse and energy in the freight, in the rail market, and if we consider that surely also the road transport was able to react to this competition, the rail was not in the position to win what were the goals that the European Union wanted. So we have to find other ways to give impulse to rail. We can say that looking at this data, it's the rules that we have introduced were not sufficient to reach the goals, and we have then to identify other potentials. And one of the potentials that we think that we could use is the introduction or a better use of the best practice that we in Europe, in the different countries that compose Europe, that we can use to give this better performance to the railway traffic. And here in these last 3 points, we can read that one way is that we have to be we have to identify potentials that we have. We have to be more cohesive in our countries between infrastructure managers and railway transport companies. And last but not least, we have to share best practice. Because with best practice, we can gain production without the use of, without needing large investment. And in this way, if we introduce best practice, we will reach a more uniformity in our countries. Last words on this principle is that the use of best practice is surely not new. In project management, we talk about the sharing of best practices. The sharing of best practices is where and will be done between the countries, but in my opinion, this is done nowadays only between some countries, and in particular between the countries that speak the same language and that have the same culture. Because if going to compare countries that have different languages and different cultures, we see that this exchange of information, we have got it, but it's not so practiced as it should be. And this exchange is limited because in most of the cases are only a little part of the person in each country that can profit of this exchange of best practice and of experience of other countries. So this was the theory. Now I go in a concrete example that we have had as SPB. As I said, we are starting to consider what we will do in the future rail renewal in the Gotthard-based tunnel. You have to consider that Switzerland has never had high-speed lines. The first one was the Badstetten-Rotritz, that is between Zurich and Bern. And on this line, that is not really high-speed line, our trains can travel till to 200 kilometers per hour. And this line was put in service in the year 2004. And we can say that since 2004, the Swiss has adopted the same way of working and the same rules that had Germany. And why this? Because Switzerland is mostly German-speaking, so they had contact with the colleagues in Germany, and they used the regulation that was used and is still used in Germany. As we started to consider how we would have done the renewal in Gotthard-based tunnel, we saw that this, if we would use the same methodic, we would have needed a lot of work windows or outage. And in the Gotthard-based tunnel, we have not the same situation as in the line between Bern and Zurich, because the Gotthard-based tunnel is the longest tunnel in the world, and with 57 kilometers, and we do not have the same, we could not organize the same logistic that is provided on the Mattstetten-Rotritz. So on the Mattstetten-Rotritz, the rail are changed and bring back in each work windows. So this way of working is very expensive in money and in time. So we said that we had we have to find better ways to reach better production, and we thought, and we have proved, because we did two different studies. One was done from us as SBB infrastructure, and the other one was done from an external project engineer that is specialist on track works. And now, because we did a comparison months ago, we are happy to say that our consideration were maybe correct, because we reached the same results. So the problem is that to reach a good production in the rail replacement, the best way is that we have to put the new rails before the working windows to do the replacement. And as I said, in Switzerland, this is possible using the existing rules with a speed not exceeding 160 kilometers per hour. And we were confronted with these rules. We started with a small way or an easy way to reach the goals that we wanted to have, with the comparison with the Italian, because I am Italian, so I know a lot of people by Rete Ferroviaria Italiana. And we did a comparison with the colleague in France, because they have a huge number of high-speed lines. And we find out that in Italy they can leave rails if the speed do not exceed 250 kilometers per hour. In France, they can be with the speed not exceeding 300 kilometers per hour. In France, they have to use some adaptation to do this. We put this consideration to our safety department in the SPB, but it was not accepted because they said that the situation that they have in Italy and France is not comparable with our situation in the Gotthard-based tunnel, because we have the lap track. So we tried to do a comparison with the Lochberg-based tunnel. They have the same system as us, but unfortunately they did not have found, or they were not so in depth with finding another solution as that I've mentioned that it's used on the Matset and Rostrit. So we said, well, now what can we do? Because if we, I think that every of you think that the rail do not move if trains go speed in the very speed with very good speed in the tunnel. But we were confronted with our safety department that said, but we cannot say. It can be that the rail have little movements and then they go in the profile in the danger area, and so this must be tested. So we did a little study. We find out that the cost of doing this test would have been about 100,000 Swiss franc, that is to say about 100,000 euros, so not so cheap. We had a lot of fight in terms of the infrastructure because this was a big sum that we have to use. But we could also demonstrate that if not doing this test and then remaining with the existing rules, we would have spent about or pay about 2 million Swiss franc only in putting fixed point to keep the rail safe when passing commercial trains. So we said there's a clear advantage if we do the test. We organized it, and we were imposed to do it in the January-based tunnel. You can imagine why, because the gutter was partially closed due to derailment, and we had a lot of pressure because for politics, if we have a problem in the January and we have also problem in Gotthard, there will be a problem in the on the axis north-south in Switzerland, but we find the courage to go further. We organized test at our risk. We decided to use rails with 18 meters long. I explained with why this length, because there was so big pressure that we have to keep an intervention vehicle 20 hours a day for the entire duration of this test. It was 49 days, so it would have been a big expense for our sector. And using an 18 meters long rail, we could have used our typical vehicle for the maintenance, so with no costs. The rails were put in the middle of the January-based tunnel, where we proved with our colleagues of the passenger high-speed trains that we have, in this case only the Giruno train, can reach the speed of 230 kilometers per hour. So this is a plan that shows where we put these two rails. We decided to use two rails because we wanted to find an answer that could have been useful for the future replacement, and we wanted not to have an influence on the technique that will be used from the executors. So if the executors will want that the rails stay between the running rails, we should have had the answer. And this also in the case when the rail would be put between the rail and the platform of the tunnel. As I said, we had to prove that the safety was guaranteed, and we must put these steel rings at both ends of the rails. There is in figure 13, you can see how were she realized, and we put a distance between these rings and the rails, because the rails must be free, so could move in both the three direction x, y, and z. We installed a monitoring system, of course, because from our points of maintenance, we have to prove every moment if the rail had moved. And to monitor the position of the two rails, we used crack sensors with a very high accuracy because we wanted to prove of if the rail had moved. So the accuracy was 0.1 millimeter. And we had problems with battery, with the energy to make working the sensor. So we decided for sensors that could work with battery, because there is, of course, electricity in the tunnel, but cable in on the platform would have caused problems for the maintenance activities, and so we take this decision. Another parameter that we had to measure was the temperature, because we wanted to see if the temperature would have had an influence of the possible movements of the rails. We put 3 sensors for each rail, as you can see in figure 15. One was at the beginning, one in the middle, one at the end of each rail. And so this was the installation of, or the plan to realize this site test. The measurement where we wanted to measure the movement, the possible movements, at least every 2 minutes, because we wanted to do at the end of the test a correlation between the possible movements and the train that would have passed in the tunnel in the duration of the test. For the safety reason, we defined three thresholds. The first was 5 millimeters. So this was monitored from remote, and we could get data. And if this threshold would have reached, we would have started with an alarm to the intervention, but not going in the tunnel. Then we define an intervention threshold. So if the rails would have moved 15 millimeters, that means that the rail would have reached the ring steel. Then in this case, would have started, we would have had the meeting and decide if we should go in the tunnel and take the rail back. And the third threshold was more than 15 millimeters. In this case, means that the rail would have take off the steel ring. And in this case, of course, the intervention would have gone suddenly in the tunnel. Here are some pictures of the installation shift. It was in the middle of June. We put the rail, as you can see, we put the ring at both ends of the rails. And then we mounted the sensor. It was done at the beginning and in the middle of the rail. We realized a steel structure to protect the sensor. And here you can see what were the time that were thought to do each type of activities. At the morning of the 18th of June, this was the situation. So with the 2 rails that were in the tunnel, and we started with the introduction of a speed reduction of 160 kilometers per hour, because the existing regulation says that we could do this till this speed of the trains, and we give advice to all train drivers that in the time of 1 week we would have had this speed reduction. Then for another week we would have had a speed reduction to 200 kilometers per hour, and if naturally the test was successfully developed, we would have then raised the speed to 230 kilometers per hour. And so we did the different steps of increasing the speed, and what can we say? That in this period we had of 49 test days, we had a total of about 7,000, almost 7,000 trains that traveled through the test site, the most of which were a Regio Express train, but also the other type of trains, intercity and long distance trains, were a big number. And as you can read, we had about 3.6 million tons that passed through the test site in this time. We got information of every type of train that traveled in this position, and here is you can see an extract of the information that we got from our department that has to do with the train circulation. As you can read, we wanted to know the time when the train passed in the point, and we wanted to know if it was which type of train was, and the other very important information was what was the weight of the train. At the end of the test, we removed all the equipment that we use in the test. Here are some pictures of what we did. And in the morning of the 6th of August, the Ceneri Base Tunnel was again could be fried for the execution of the commercial service with no speed restriction. What can we say of what we did? That, of course, there was no significant displacement, but today we say this with no thoughts, but at the time we were not sure if we would have had no displacement. And we never reached the threshold that we put. And what surprised us was that the big movement were in the z-axis. And this was in the case of the rail put in the between the platform and the running rails. And what we find was also that there was no influence of the temperature. If we show in details what was the situation of the sensor between the rails, here we can see that in the y-axis we didn't have a big movement. The bigger one was only in that direction, as I said. And if we look at the sensor between the platform and the running rails, also in this situation, in the x and y-axis, we didn't have any significant movement. Only in the z-axis we got this. Then we did, as I mentioned, a comparison between the displacement and what was the rail traffic. The measurements were done every 2 minutes, so we could construct this type of comparison. We took one sensor, and we looked at that there was some movement that we didn't find a reason why we had this movements. And going in details of the data that we got, we took the sensor C13 and we looked in the movement that we had in the y-axis, And as you can see from the figure 30, this in blue are the movements that we have got, and with the orange point is the moment at which the train passed through the site test. Here you can see the type of trains that passed and had a big weight, more than 1,000 ton. This was not so clear, this representation, so we did a bigger one, considering only the first six hours of the test. And if you look at the orange point, you see that the train has practically no influence on the movement that the sensor registered. So it was possible to say that the movement in the z-axis that we have seen that could be explained as if the rail would have flight were not caused from the running trains, but they were caused from other factors. And in particular, we think that it was caused from the dust, from the pressure of the air in the tunnel, and not was caused from the train, the passing trains. So the test, in our opinion, proved the success that we can leave free rail till a speed of 230 kilometers per hour. We had, at the end of September, a meeting with our safety department, and we are very happy to say that they say, okay, we accept this result. You do not have to put safety measure if you leave the rails in the tunnel. And they give us these activities. We will start it next week. We have to develop a railway safety risk analysis. This so-called key 250, Concernleitung to 250, because we have to mention what we did in this test. We have to explain all what we have measured, what we have reached, if we have to do comparison with the other infrastructure manager. And at the end of this proceeding, we have agreed that in the year, it was not possible before, but in the year 2026, there will be a modification of our instruction, internal instruction 22211. And we are very glad to say that we hope that in 2026, also by the Swiss Federal Railways, we can leave free rails till a speed of 230 kilometers per hour. This is regarding the ZEP structure that we have in the tunnel, and for what it means, the outside section before and after the tunnel, we are authorized to do a benchmarking with our other railway infrastructure managers. And also in this case, we have to elaborate to describe it in this key 250, and it will be then integrated in the internal rules of the SPB. Some consideration of me, the use of this practice, or in general, not only talking about rails, the use of best practice will surely give an impulse in the development of the modal shift from road to rail, but it will be surely not sufficient. Because, of course, the best measure is to realize new railway lines, and above all, if we give the so-called reticular shape, so that the entire network is very flexible. And of course, if we look back at what I said at the beginning of this presentation, it would be very nice if we reach the same goals that were done almost 200 years ago. And I think that this is a paradigm that in Europe is not done. We are till today we give money, more money in the rail, but not so enough or so many as rail should have. Other consideration is that, as I mentioned before, the best practice will give are not expensive because each of us has his practice, and if we share this with not big investment, we will all better. But this is not the panacea of what are our problems. And here I mentioned rail, but before coming in this role by the Swiss Federal Railways, I was in charge of the planning of the maintenance activities in the Gotthard-based tunnel, and I have seen that there are many other fields where we can improve best practices, and we could do this, and it's very, very incredible. Also in the new technology that we are introducing, and that will be referred in the next presentation in this conference. So, in this representation, we are not alone. We do not have to think standalone. We have to share our experience. So, and we have to define goals, and compact, we have to go in the right way that we have defined together. Now, I go a moment back. In this picture, I clear where is this fellow. This fellow is Marco Corradini, so I am. This is a picture that is more than 10 years old. Here, I want to show this picture because here I was in Germany, as you can see from my dress. I did one month's holiday in Germany, working on the network of DB. I was by DB International. Of course, my wife was not happy because I used my holiday to go there. But I think that at the time I was working for Alptransit, so a Swiss company. But what I want to say is that it's important. We have talked about interoperability of infrastructure, interoperability of vehicles, but it's very important also the interoperability of people, because if you don't have, we don't share, we don't learn from others. And what I want to say is the mindset, not the if I am Italian, I work in USA for an Italian company, because the mentality is always Italian. You have to go abroad, and this is the best way to learn how the other works. Of course, we cannot do this in all the countries that are in the world, but I think that at least the countries that are our neighbors should be a good possibility to improve and enlarge our knowledge. Okay, so in this situation, I think that the association, the railway association, as chief, as UEEIV or VDI or a GDI or other one, are surely very important. And I want to conclude my presentation with this consideration. We have had many regulations the last 30 years. I think that we have to better apply what we already know and what we already have. And what I think is also important, that we have a very important, strong central coordination, because we have to go in the same way as I showed before. And sometimes we have what I see nowadays is that we are losing competence, and I think that we have to find this again. And so we have to be more concrete, determined, efficient, and effective. And this can be done, I repeat myself, in the choosing of the best technology and the using of the best organization that they could have. And in this representation is I can summarize my consideration. If we use the best of what we have, we will surely reduce the differences between us, and if we reduce the differences, we will have a better interoperability. And this is a reinforcing loop that, if it goes on, it can give only benefits to all of us. And if you look broader, the little differences will produce also that the rules are the same or will be the same. Actually, we need time in the different countries, and this will help the interoperability. And then I take
Marco, please, could you speed
sorry.
up?
The last point for me is this one. I take this example of what we do today in the rail. The rail are 53 times safer if you compare the deaths, and 150 times safer in the accident in comparison with the road. So I think that in the last years, last decades, we put a lot of priority in the safety. Safety, I'm a transport engineer, safety is position 1, punctuality is position 2, but in the moment the priority for me is that we have to put our main goals on the transfer of modal split from road to rail. This is the last one, and here are my contacts if there are questions after the conference. And so this is my contribution to this conference. I hope you appreciate my speech. I hope to give you a concrete example. Thank you.
Thank you, Marco. We are a little bit late, a little bit behind schedule, but no problem. I hope the other ones could speed up. I would hand over to our next presenter for this session. It's Professor Brügger. He's a consultant from Switzerland, and he will give us his vision of a safe rail freight transport.
Good afternoon, ladies and gentlemen. Welcome to my presentation about a vision of a real-time freight train monitoring system. Instead of this ERTMS written on the slide, I use a simplified abbreviation RTF. Third, my English is very bad, but I will give my very, very best. I hope I can give you an insight into a dream or a vision for cyber freight transport, a vision that could be realized in the relatively near future. With my presentation, I go back very deep, not in the high level, I go deep to the freight wagon. Introduction. European rail freight transport involves a great deal of effort, including the creation of train compositions. With the railway companies' existing infrastructure, equipment, especially for freight wagons, it is very difficult to save costs and time and still achieve a much higher level of safety. The deficiencies in the reliability of the wagon very often lead to derailments and usually cause immense damage. There are 16 measurement centers in Switzerland where value quality characteristics of freight wagons are determined. These measuring points are stationary and therefore only recording at one point in time while the train travels through the stations. What happens in between, you can only be recognized at the next measuring station. With my vision, I am pursuing a way of carrying out continuous measurements, processing the data obtained in real time and transmitting it to the locomotive. The data is transmitted via the GSM-R network, permanently assigned to the railway. Signals that are already determined by third-party manufacturers of assemblies are also to be included in the process. Initial situations facts. Excuse me. I'm Simon. Okay. In European freight transport, there are probably smaller or larger incidents of damage, mostly derailments on a daily basis. At international level, only incidents with damage amounts of several millions are communicated. Smaller incidents with loss of a few tens of thousands of francs or euro only published regionally. I'm referring to a few cases of derailments of freight wagons, but I am restricting myself to incidents in Switzerland. In summary, the few incidents show the enormous costs caused by an accident involving freight wagon without reference to passenger transport. On an international level, enormous damage of several trillion euros can be expected even over a short time frame. Case 1. On January 4, 1991, 8 of 14 cistern wagons, each carrying 85,000 liters of petrol, derailed to a broken wheel at Stein. Stein is a small city in Switzerland, while a block train was passing through. Some of the wagons sprung a leak and the major fire broke out. It was an enormous inferno. Damage several million Swiss francs. Case 2. Derailment of a freight wagon on a switch at Zurich in 1994, approximately 5 kilometers from Affoltern in the near of Zurich. The freight wagon lost a wheelset bearing at the 7th position in the composition and derailed. The second axle of the wagon also derailed and the wagon overturned. Other wagons also carrying fuel caught fire, causing an inferno and property damage running into several million Swiss francs. As it turned out, the incident was the result of a material wear fatigue. Case 3. Daniel and Markus, we worked in the Gotthard tunnel. Derailment of freight wagons in the Gotthard new base tunnel in 2023. After entering the tunnel at the south port of freight wagon derailed to a broken wheel disc approximately 7 kilometers before the high-speed switch. The wheels traveling next to the rail destroyed the switch mechanism and released the locking mechanism. This caused the points to jump over and the train to break up. The tunnel interchange gate was broken by an impact. In addition to replacing this tunnel interchange gate, the track systems had to be replaced over a length of approximately 10 kilometers. In addition to the disruption of the transport link for over a year, the cost of the installations totaled several 100 million Swiss francs. More details can be taken on my slide. Case 4, as an example of minor damage that can be overlooked in I would cite on an incident in the Bern-Fribourg line last September. As you can see from the slide, the major impact wasn't material damage, it was restriction on passenger traffic. Further details on the slide. As a result of these terrible events, the infrastructure on freight wagons must be significantly improved using future-oriented technologies in order to increase the safety of freight transportation by rail. These facts, among other relevant aspects, lead to the following processes which should take place in real time. Okay. Source of interference and monitoring. Of the points listed here, I would like to focus on a few particular points. Damage to the wheel, which can lead to wheel breakage, vibration of the bearings, vibration at bearings due to imbalance of the wheels caused by wear. Deformations of the axles caused by several physical events, some of which occur together and some of which are independent. Horizontal displacement of the load, shift in loads due to the shift in freight. Wagon combinations, coupled wagon. Based on the incomplete list of possible error sources in the previous slide, the following requirements can be defined for a real-time control system. Requirements for an early detection and monitoring system. General information on understanding the vision. RTF. The vision system is based on a 4-layer model. Layer 1, sensors. Layer 2, processor system for recording, monitoring, and evaluation the sensor signals. Layer 3, processor system for coordination and communication between Layer 2 and Layer 4. Layer 4, integration into international rail operation control system. Short principle notes placing the 4 levels. Let's look at the lowest level, level 1, the sensors system and the actual vision system, level 2. Integration and into a freight wagon and the relationships between the physical variables and the sensors. I don't want to go into details about the sensors. The additional monitoring and the processes running in parallel on the actual submodule level 2. The basics can be found on the following pages. In the block diagram, assignments and relations of mechanical elements to detection opportunities with complex future-oriented sensor systems. Details must be specified in the implementation specification. You see all the details on this slide. I will not go into details. Layer 1 to layer 4 in freight train composition. The RTF top module, layer 3, is placed in the locomotive and serves as a link between the International Rail Operation Control System and the RTF layer 2 submodule. Further management tasks to be defined in detail are carried out in RTF top module layer 3. There is also an interface to display for the locomotive driver. Representations and operations options on the display must be specified. The locomotive driver himself does not intervene in the administration via this displaying during normal operation. All decisions are made by the International Rail Operation Control System. Values can only be transferred from layer 3 to layer 2 submodules by the locomotive driver or train composition manager via a special personalized access authorization. Layer 4. Implementation of the RTF in the International Railroad Operation Control System. A communication and management software package is implemented for this purpose. The structure and scope of this software is part of the planning on the RTF. Multi-layered structure of RTF. Let's take a moment to look at some of the key aspects of the system. As shown before, the RTF is conceptually based on 4 layers. Information to layer 1, see above, we've seen. Here is some information on the details of the layer 2 submodule. As you can see in slide layer 1 before, slide before, each submodule layer 2 handle 2 axes with functions on slide. Here, each submodule can handle 2 axes. What's submodule or level 2? Level 2 is a single board computer based on digital signal processor and FPGA. Sealed housing that must meet the requirements of railroad technology. Additional closed housing as a cover to protect it against stone, shipping, water, rust, and so on. Power supply in connection with sensors. Not the separate power supply. Power supply is in connection with sensors. Redundant supply unit is supported in the device by gold caps and rechargeable batteries. The signal processor records all sensor passes and processes the signal in parallel structure. Processed, calculated, and evaluated signals are stored in a memory with additional timestamp. Parameters and labels are also stored in a separate non-volatile memory. All parameters, limited value, time, and so on, and markings can be entered directly on site in a password protocol protected programming mode or directly via the layer 4 rail operation control system via the GSM-R rail network. The stored calculated values together with the identification data can be called up at any time from the central computer layer 3, which is located in the locomotive, or under special circumstances directly via the International Railroad Operation Control System. Recording, calculation, and checking. Recording, calculation, and checking the plausibility of the sensor data received. On the left side, in the representation of a sensor path of a shaft with principal representation submodule layer 2. On the right side, you can easily see how bearing damage can actually be detected. You see, this state-of-art technology now not so easy to implement in RTF. Sorry. Recording, calculating, and checking. It would be possible to design the system in such as a way to the freight wagons can also be tracked at any time, location data available at all times, as long as the battery support energy supply is guaranteed. Such variants are possible. The latest technology must be implemented to the planning, development, and manufacture of various sensor systems required to the RTF. The designs and developments of the submodule layer 2 and also level 1, the sensors, and the superordinate top control system layer 3 must meet the safety and railroad technology requirements in addition to all the mechanismal stresses. The vision of a real-time freight train monitoring system can become a first step towards a digital, real, and safe world of international freight transport. It's now time to take this step together. I would like to mention a few more facts about the RTF project in short form in the next few slides. Supplements to my comments on my chosen topics. Cost horizons, implementation steps, international certification. Steps for this design for a RTF. Preliminary clarifications. Creating a specification sheet. Simulation in the run-up to developments in the field of sensor technology. Development of the subsystems. Installation in the freight wagon, installation in the locomotive, pre-commissioning test, revision after the pre-commissioning test, international improvement and of submodules and top modules, and sensoric, production of the system, installation of the systems in freight wagons, installation of the systems in locomotive, tests in real freight traffic, commissioning on the installation with integrated firmware, software, and the connection to the International Railroad Operation Control System. Parallel to the steps mentioned here, the implementation in the communication with the International Railroad Operation Control System takes place. Summary. summary. You see, as a template of the development of the RTF with very high requirements in the railroad technology environment, I show here the cockpit display panel placed in a helicopter. The hardware and firmware developments are subject to MIL standard requires and is completely designed from me. RTF is a major challenge due to its complexity and requires in-depth knowledge of railroad technology, electronics, physics, and digital signal processing, including mathematics. I think about Fourier transformation. Also, the environmental conditions in freight wagon operation are also very demanding. This problem can be overcome. Using such complementary knowledge, the RTF can also be developed, built, installed, and operate with a clear conscience. Future prospects. The introduction of automatic coupling on new freight wagons will be a major step forward in the future. Thanks to these coupling systems, electricity and data lines can be connected automatically in addition to compressed air in the future. However, we are talking about the present here, this time, not the future, about an existing freight wagon infrastructure with many variants, older or older poor. The concept of my RTF will be equipped in such a way that all existing signals and the power supply can also be fed into the lines. I am aware that different companies are working on many different projects that are of interest to the problem of safety in freight wagon transport. Very important requirements and regulations also from Admin Suisse. I see my vision as a real-time control, evaluation, and monitoring of the technical execution of freight trains. Please ask questions direct, face-to-face, not here. Thanks for your attention.
Thank you very much, Professor, for your vision. I would hand over quickly to the next presenter. It's Mr. Fabio Senesi. He's head of R&D at the Italian Railways, RFI, and he will give us an expertise of ERTMS from the first application to a new technology strategy in Italy. It's your floor.
Good evening, everyone. I'm Fabio Senesi from RFI, the infrastructure manager of Italian Railways. I'm here to share with you some experience about the introduction of ERTMS in Italy. And I hope that in Bulgarian Railways that starting to this experience, it should be some good idea about how to deal. I'm responsible at the moment of research and development, but for many years I'm involved in this project. Italian infrastructure is plenty of viaducts, tunnel, and many cities. So we have a complication about anthropology and also geomorphology. And but we introduced in the last 20 years many technology. This technology is coming from safety, coming from obsolescence of previous one technology, and also obviously by introduction of safety. Safety means automatic protection of a train against collision. So we have a Class B system in main of 13,000 kilometers. We have ERTMS introduced by 2005 for interoperability, but also to reach 300 kilometers per hour. And we implement the GSMR for, again, around 12,000 kilometers of lines, and electronic interlocking. So the target by commission, by regulation that this morning we heard about it, is to complete the core network by 2030, the core extended network in 2040, and the comprehensive network in 2050. So the core network in green, the extended core network in blue, the comprehensive network in yellow, and often the remain network in red is shown here in our picture of Italy. So the 4 different kind of network must be integrated, because the commercial railway is not divided, comprehensive by core. So the approach was the idea was to a system approach. In 2005, we opened the first high-speed lines in the world by radio, using ERTMS level 2. The idea was to eliminate any fallback system, so the high speed was realized without light signal, without fallback. It was a winner choice because we enforce the system, the availability of the system, and now we have a large success in commercial also. We, as you perhaps you know, we have 2 competitors. To the incumbent company, Trenitalia, and also the private company, Italo, that are using ERTMS for commercial issue. And we continue to introduce in high-speed network ERTMS alone. So at the moment we have 1,000 kilometers or network using level 2. Not only ERTMS, but also conventional lines. In conventional lines, we have the legal obligation that I showed you before, but we want to use this obligation also as a strategic opportunity, because ERTMS is not born for high speed, it's born for conventional lines. The main issue of Commission is interoperability, but we don't want to use only this opportunity. This opportunity is to increase performance, increase safety, and using also innovation coming from Europe's rail for the future, for introduce a system that has been looking forward for the future. So we have a many important issue for the new baseline. I don't want to stay a lot here to explain, because our baseline in high speed was the baseline 2. Now we have the baseline 3, and tomorrow also the baseline 4. So the portfolio application in RFI, and not only in RFI, in Italian network, is a lot of kind of ERTMS. We don't have only high-speed lines. We have needs of capacity in the urban nodes, introducing the high density of hybrid solution, to have a little section, and to add value of infrastructure asset. We have the corridors. We have the regional lines, where we have a lot of level crossing. To control the level crossing, the radio is a beautiful opportunity. We have the need to maintain track and train compatibility, And coming from the operation, we have an opportunity to use a log file integrated analysis, because when a train stopping in the land, you want to know who is the guilty. If it's a train of infrastructure manager, you have to check a lot of data. So the engineering of automated log analysis is another big field of digitalization, and in particular of ERTMS application. The opportunity of decommissioning of previous system was a big debate in Italy. When I put the new system in a greenfield application like high-speed, okay, is an easy choice. When you have to choose to eliminate the previous system, introducing the new one, decommissioning the other one, there is a big debate. And to arrive to the strategy to put the only one system and eliminate the previous one is the new strategy that I want to show. We compare 3 scenarios. The basis scenario, so we continue without decommissioning the system. The intermediate scenario with decommissioning from 2027 when we put ERTMS without acceleration. And the third scenario, scenario B, we want to do the whole network, decommissioning the class B, and anticipate the acceleration, not waiting 2050 by European target, but arriving in 2040 with all the network. We put all these 3 scenarios by a cost-benefit analysis, by economics, and the third scenario has a net present value of 3 billion respect to the scenario 0. So it's not only an opportunity of interoperability, safety, performance, there is also economics to put a radio system instead a previous cable system or electromechanic system. So we pass from a dual trackside strategy from a dual onboard strategy. It's clear that you eliminate heavy on the track, but you put more complexity on board. And coming back to the presentation of Marcus, the complexity is on board. And not only the command and control, the complexity is the rolling stock. The owner of rolling stock is not part of the play. So we have to make a memorandum, an agreement with the owner of rolling stock, because you put complexity in the rolling stock with someone that is not part of the play, saving money on track side, and we have member states that give money to member states, to the infra manager, Europe that give money to infra manager, and private people like railway undertaking that has no money enough. There is an owner of rolling stock that is not part of the play. So this is the real complexity to solve. How to deal a synchronized investment on track side and train borne, giving the same opportunity to railway undertaking and infra manager. In Italy, we try to do it, but it's a country solution to put on the field the money for the track side, to have a special law to give money for a railway undertaking, asking to commission. They say yes, but it's a country solution. For me, is needed a European solution. You eliminate a light signal on track and you put on board. So the investment, why is only given money for infrastructure manager and not for railway undertaking? We make, due to a pandemic period, a recovery fund. when the recovery fund asked to Italy, do you have a plan? We put the acceleration plan. They give us 3 billion in the recovery fund to realize 3,000 kilometers of ERTMS, standalone, radio-based. And so we start with 2 big tenders in 2021-22 with a integrated technological tender, so not only ERTMS, but also interlocking, telecommunication, traffic management, to start with this new deal and to have also money to help the railway undertaking. This is how we divided Italy in different lots, in different segments, with different suppliers, to start this new strategical investment. So you can see Sicily, you can see Sardinia, so it's not only core network. It's a nice slide. So it's a network is a tree. We don't want to only do the root or the core, also the leaves. And how to deal the complexity. RFI is managing the type. We have 100 type of train, first-class train. We pay for update from Class B to ERTMS, it is 100 type. We already realized 40 type. And we ask to government to give money for the fleet. Otherwise, all the investment on track side is not sense. The main bottlenecks is the rolling stock owner that say, I'm not part of the play. You put in my train something, I want something. And this is a problem. So, just to finish, ERTMS in a nutshell. We start with safety, because our agency asks more and more and more. And we say, okay, we put the best, ERTMS level 2, okay? We have a need to be a single standard because we want to simplify our network, possibly digital and radio. We want more performance, speed, capacity, flexibility, holistic design, and modal shift toward railways. We want to put in the same field of the other country in innovation, so Europe's rail, about talking about ATO, the future of technology. So ERTMS is the player. We want to save energy because ATO saves 20% of energy. So we know that we want to coordinate trackside and onboard unit by consultancy, continuous, permanent, with all the stakeholders. We know that we have a jump, a cultural jump, because people that arrive with a cryptographic key instead of an electromechanical system need a cultural jump. It is an extraordinary opportunity for supplier, for all the stakeholders to have a significant challenge for the future. We have a benefit from CAPEX and OPEX. And then, last but not least, we can reach money from Europe. Because ERTMS is part of the Green Deal. Thank you for that chance.
So thank you, Fabio, for your very interesting presentation. I think you are in a good way to promote ERTMS in the future in Europe. I think one of the most challenging thing we have to do. Also, thank you for speeding up to give us some more minutes for our last presenters today. I want to introduce to you, we have a couple presentations. Mr. Andreas Wenz, he's from Austrian company Getzner. He's working as a project engineer, and he will give his presentation together with Professor Ferdinand Pospischil. He's the head of the Railway Infrastructure Design Department of the Technical University of Graz, and both of them will give us a presentation on a special infrastructure topic which is related to the track. So will give us opportunity to speak about maximum track availability despite cost optimization. Please, Ferdinand, proceed.
Thank you, Bernhard, and thank you everybody to stick with us to this last presentation of the day. We also want to speed up, so in the end you can go to the dinner, but be sure before we are all at the dinner party won't start. So we've heard a lot today about interoperability in the railway system, but now we want to have a look from the overall perspective. And as we've heard today from Michael Walter in the morning, in the track there are some requirements, and he was talking about the structure gauge. And I would say the structure gauge is not the only issue for interoperability. It's also the gauge of the track. So we need, of course, we need the same track gauge to do interoperability, but not only that, because that's quite clear. To do that, we need some extended options for the reduced maintenance, because if you want to have traffic, and we've just heard this from the colleague from RFE, we need increased performance, and for performance we do need some options for reduced maintenance as well, and to have availability of the track. To have that, we should have a look at the rail profile and at the wheel profile of the trains and the track, and of course have a look into the rail inclination. The next thing is, it would be very nice to have a homogenized traffic speed and a kind of traffic. So on the one hand side, the commuter trains, and then the freight trains on the other side, and the high-speed trains. And all of that would then result in a high track availability, which would give us the opportunity to have a Europe-wide interoperability railway system running. That is theory. Let us have a look in the world as we see it at the moment. This is what AI gives you if you say, I want trains in Europe running around. But this is basically also what we experience every day. Not so much running into the east side, into Russia nowadays, and we don't have those long lines anymore. But ÖBB is running very well on the night trains to re-establish all of that. So what is the real life? We have mixed traffic in use rather than pure traffic on the track. And one thing is, we have one wheel profile, and we face all of the different types of rail profiles in Europe. Just imagine one cargo wagon starting in Spain and running all the way up to Scandinavia. So we have this one wheel profile, but it runs all over Europe, and everybody has some different rail types, just starting with the 60E, 1, 2, 3, 4, whatever. Then we have the 45E something, and so on and so on. So we have so many different rail profiles, but always the same wheel running through all of them. And the rail inclination also varies between the different countries. So all that, in the end, coming from that, the reality is we don't have that smooth running system, but we have a very high wear, and we have high track dynamics within our system. So let's have a look at those track dynamics and where those come from. So I show you here a little result, a measurement, showing you on the vertical axle the vertical force, and going up you see the sleeper deflection. So what you can see here, of course, if you have more vertical force coming from the train, you would also see a higher sleeper deflection. But that's not the only thing you see. The different colors represent different sleepers, and they are lying next to each other. So the thing is, if you have one sleeper, if you have one train running here, all those dots basically on one line from the top to the bottom represent the same train. But that means having the same load, the deflection of the sleeper is very, very different from one sleeper to the next sleeper. So why is that? What happens here? Or let's have another look on the twist of the sleepers, and that's the same thing as I showed you before. We see the axle load, and then we see the twist, and we can also of course, see the twist is very much dependent on the axle load, but also on the type of train running. So, of course, a locomotive, quite heavy, has a higher twist than a suburban train. So what happens and why is that? This is because of that. We do see ballast breakage, and we do see a different way of reaction of the sleepers in every situation, and every situation means from sleeper to sleeper. There is a difference from sleeper. Every 60 centimeters you will face a different environment. And I will just show you some pictures of this environment that I'm just talking about. So as you can see here, this is the downside of a sleeper, and I would say there could be some ballast cleaning in the next few days maybe, and that would probably increase the system and the lifetime of this whole system. But at the moment there is a high stiffness in the system because there's a lot of fine dunes within the ballast, so there's no proper load transfer from the sleeper into the ballast and into the subgrade. Well, let's have a look at this system. What can you see here? This is a track running apparently under a bridge, so you can see here the shadow, and you have some white spots within the ballast. So there's a high dynamic happening. The ballast is worn down. You have hollow sleepers, and of course they are marked already. So this is a picture that is going to change probably a few days after it was taken. So this is the last stage of the lifetime of this particular area. But why is this happening? Here it's happening because there is the subgrade is not stable, so there is different stiffness within the subgrade, and this reflects up, and then the ballast is going to be destroyed because you always have to look at the whole system. And this is basically, if you have a close look in this area, how the ballast and the system reacts. So you see the train passing, you see those dancing little ballast dunes, and with these dancing ballast dunes, of course, you have high dynamic impacts, and those dynamic impacts will reduce your ballast, will give you ballast wear, and this for your ballast will have to be changed. You need to change your ballast, and your availability of your track decreases. In the end, if you don't do anything, you can see here a lot of fine dunes in the middle of a sleeper. So this is basically a concrete sleeper. You have a lot of fine dunes. So basically, your elasticity of the whole system is not there anymore. So you get breakage where you don't really want it because you have a force coming from the sleeper onto this into the middle area where you normally would not want to have the connection. In this picture, I want to stress the points that I have taken before. So you do see the ballast hardness. It has nothing to do with the bedding modulus, but ballast hardness basically in this time is if you go with a tamping machine, and the force needs to the force that the tamping is needed to compact the ballast is written here, and this is a real track, and this is the force that is needed, or basically also the we call it the ballast hardness. And as you can see, this is a worn track. It's not a new track, but still, it differs a lot from sleeper to sleeper. So this is what we need to keep in mind, that we're not talking about slab track where everything is the same. We're talking about some material that we just throw into our track, and then we want to tamp it, and then we hope that it's kind of a smooth area. This is what it's on the end of the lifetime. It's not. We are talking about a very flexible way of track bedding. Let's call it that way. So what do we have for challenges? As you have seen before, bridges, we have transition zones, we have turnouts, the superstructure components vary, and of course if you go from one rail type to the other rail type, you get a dynamic impact. Easy. If you have a change of sleeper type, you will get a dynamic impact. If you have an isolated joint, you will have a dynamic impact. If you have rail welds and they are not maintained properly, you will have a dynamic impact. And whenever there is a dynamic impact, you stress the whole system. And when you stress the system, your weakest part will say goodbye quite fast. And the weakest part is the ballast. So with those different local bedding modulus, as I said, we have the dynamic impacts, we get the ballast deterioration. Then we have the hanging sleepers, as you've seen before in the short video clip, with reduced damping effects. With the reduced damping effects, we get the sinking track quality. And with the sinking track quality, again, you have a different bedding modulus, and then the whole circle starts from new. So once you start with this circle, it's really hard to stop that circle. So what we need to do, don't let this circle start. So the question now is, what can be done? How can we stop this circle from starting, and then by not starting it, having this high track availability? Of course, the easiest thing, don't change anything. Do one system from Naples up to Stockholm. Theoretically interesting, practical, no. We do need a homogeneous subgrade. That is also a nice thinking, but just think of how many bridges, little things you need to pass through the track. So there are so many disturbances in the subgrade that need to be covered. We should not do multiple changes in one position. So don't change your sleeper type and rail type and subgrade type, maybe ballast type, or even coming from one type of, for example, slab track to ballast track, all in one position. Do a transition zone. Just do it in a kind of spread out area. Now coming back to the ballast, we have here this plane, and as you know, every plane is defined by 3 points. 3 points do mathematically define a plane. What does that mean to our system? We do think back to the sleeper. We have a sleeper in the ballast bed, and this ballast bed, the sleeper must be held by the ballast. So basically that means the highest 3 points hold the sleeper. And every other thing only holds the sleeper because there's a little elasticity, and these 3 points, these 3 highest ballast dunes get pushed into the other area. But in the end, still by pushing them down, you will have a contact area between sleeper and ballast of only 3 to 5%. So all your forces, which are coming from the rail, going on the sleeper, going to be sent down into the ballast bed, is on a very, very small area of 3 to 5% of your whole sleeper. So you have a high pressure there, you have high tensions, you have a high dynamic, and that's what leads to the ballast breakage. So of course, what could we do? We could start with an idea of spreading out this area. And this is where I would like to hand over to Andreas Wenz from Getzner Werkstoffe.
Thank you very much. The good news is something can be done. And the answer is undersleeper pads. So the idea is to increase the surface between the ballast and the sleeper that we just heard is very little in the beginning. So if you use a sleeper pad, an undersleeper pad that provides some elasticity, you're able to distribute that force to a larger surface under each individual sleeper, but also to more sleepers in a distance, because when the substrate or when the contact point between the sleeper and the ballast gets softer, you also get a longer bending line in the rail, which means the load is distributed to more sleepers. And this together, these two phenomena together, lead to a very much decreased pressure between each individual sleeper and the ballast beneath that. So, in fact, you can specify this or quantify this also because the ballast contact area to the sleeper can be increased up to around about 35%, and that is a factor of 7. So really a good thing to do and a very effective way to reduce that pressure. There's a diagram that shows the different types of unsymmetric movements that a sleeper can do, and also of different loading scenarios that a sleeper can endure. But all of these different motion types can be reduced by such an undersleeper pad. So within the orange area that you see in the diagram, which would be the ideal continuous contact between the sleeper and the ballast, we are in a very close area around that. So there is no toppling of the sleeper, there is no winding of the sleeper, it is just the whole sleeper moving as one thing, ensuring a continuous contact between the sleeper and the ballast, and thus also the best possible force transition from the sleeper to the ballast bed. I don't want to stress this to the final detail, but in generally, this is the result of that. What I would do rather is to show you what happens under the sleeper. What you see here is the underside of a sleeper that has been in the track or in a fatigue test rather, TC4. So that means heavy haul fatigue test for a few million cycles with a padded sleeper. You see indentations in that undersleeper pad that show you the actual area that has been used to transmit the forces from the sleeper to the ballast, which is, as you may agree by simply looking at it, more than 3%. This is, however, not permanent. But we need a material that does elastic recovery after some time, because if it did not, you could not use that sleeper after one tamping period or even in another place maybe. So you need some recovery, and it needs to be adaptable to the situation after tamping happened, for example, or after the sleeper may have been reused at some other point, or maybe the loading scenario of the track changes. All of these is possible. So we need elastic recovery, but we also need that temporary plastic recovery just to create that transmission surface. And if you manage to do that in a combination, you end up with a so-called elastoplastic behavior, and that is exactly what we can provide with an undersleeper pad that is engineered to the task. So that's the theory. The practice looks like this. We have at the left side a picture of an unpadded sleeper in the track, and on the right side a picture of a padded sleeper. And I think I don't need to explain a lot. On the left side you see the sand, the worn down ballast, and on the right hand side you see the practically virgin ballast underneath the sleeper. So there is actually a pretty obvious difference. Mind you, after 100 million tons of traffic over that single sleeper. So this is really something to be aware of. We can do, or we can make a big difference. I would like to prove that also to you from a test track that has been maintained by the Austrian Federal Railway, ÖBB, where 4 sections of a track have been looked at very closely for a long period of time. And one of these sections has been equipped with undersleeper pads. That's the one you see where the red arrows go, and that had a slight curve in it, in fact, which was the reason why undersleeper pads were used there, because curves are higher loaded than the straight track. And the diagram I would like to show you is the development of the settlement of the track in each of the 4 different sections in a period of time. So each line that goes up is after 1 year. And you see the settlement of the track increases in almost every place. And I'm asking you, guess in which sections undersleeper pads have been installed. Well, it's written there, you can see it. It's the 3rd section where it says curve and it has USP undersleeper pads. Which also means that this section did not need as much maintenance as the others. And this also is shown in a second diagram I would like to show you. Again, it's the 4 same sections, and you also see the deterioration of the track on the y-axis, and the time axis is from 2001 to 2008, so it's a couple of years. And each time you will see a notch in the diagram that looks like this. This is a tamping process. One of these lines has no tamping process. That's the 3rd section of the track. No tamping in 7 years, where every other section has needed tamping, although it is a straight track as opposed to the curved track with the USP. So also some significant improvement. This stirred up a bit of interest, so ÖBB thought we need to look at this closer, and what they did was to have a look at over 1,500 cross-sections in the track network and find a dependency of the maintenance effort by, at the one hand side, the loading of the track, and on the other hand, the curve radius of the track, because curves, you know, as narrow, the more fiddly these are in terms of maintenance. What you see is in each of the cells of this table, on the left-hand side, a number of tamping intervals. So that's 2.5 years, for example, for this first one. 2.5 years tamping interval without undersleeper pads, and 5.5 years tamping interval with undersleeper pads. And you can do that for every curve radius and every track loading scenario. And if you do that, you will end up with an average increase of the tamping interval of a factor 2.75. So more than doubled tamping intervals. That's only half the money if you think of it. And that's quite considerable saving. So there is another aspect to undersleeper pad. It's not only the technical maintenance of the track quality, but there is also an aspect of cost saving. This is long-term, of course, mind you. So this will not happen from one day to the next, but you need to look at the track life. So this is why a life cycle cost analysis has been done, which was done by the Technical University of Graz, actually, under Professor Veit. Some of you might know him already. He's quite a name in the business. And what they did was to look at first the mechanics. So how does this work? How does life cycle cost work in this place? And what you see is a diagram that shows you the track quality and when something has to be done. So there is a threshold of track quality, and you have an initial state. And this wears down over time. And if it reaches a threshold, you need to do some maintenance to get quality up again. You will never reach the original track quality because, well, components have worn down a little. So you will never get up to 100% again. And this cycle repeats for a couple of times, and after some cycles, you will not be able to improve the quality as much as would be necessary to keep it. Opposed to this, you can also have a look at the same cycle with the undersleeper pads and have a look at the difference. In fact, you can do that a little more detailed if you know exactly what is the part of investment, what is the part of maintenance, and what is the part of operational hindrances. So these three components compose the overall life cycle costs of such a track. If you do that, and this is an example from the Austrian Federal Railways, of course, In this case, for a traffic load of 70,000 tons per day on that track, on a straight track, you will find that the overall cost could be reduced to 68% of the initial cost just by using undersleeper pads. This is, of course, not true for every section of track, because you need to look at these individually. But fortunately enough, this is also possible. So the model that has been developed allows it to put in the numbers for the cost for track relaying. So this is a complete renewal of the track, or a ballast cleaning itself, or just a leveling act. Whatever maintenance effort you need to do every once in a while, you can put a number to it. That's the cost of it. And if you do that, and also know what is the average cost of the padding of a sleeper in your track, you can calculate an internal rate of return, which means basically dependent on the traffic load on the track, your internal return on the investment of the track is growing larger. So assuming a cost of 24 euros per sleeper, which is not an absolute number, so this depends also on what kind of padding you need, but assuming a cost of 24 euros per sleeper and 70,000 tons per day, you can reach an internal rate of interest in your network of 17%. And that's a lot. So savings over the lifetimes of a network is absolutely worth thinking about, even if you have some more initial cost by equipping your sleepers with undersleeper pads. Wrapped up, this means you can achieve to have less maintenance effort. You will have a better track stability during the lifetime of the track. You will have a better track quality, and you will have an overall longer lifetime, just because the weakest link of the whole thing, the ballast, is protected. Coming back to the very first lecture that we heard today from Mrs. Dimitrova, this is what overall interoperability needs. If you don't look at interoperability just in terms of technical evenness, but also in availability. To make it functional, a track needs not only to be in a technical state, but it also needs to be available. So that's the lesson I want to put in the audience for today. Availability is also part of interoperability, and it can be greatly improved just by keeping every part of the track in shape, and the most vulnerable of that is the ballast. Thank you very much for your attention.
So thank you, gentlemen, also for keeping the time. I think we have speed up a little bit, so we can finish our third session. I think it was an interesting session, which we started with thinking about best practice on an example in Switzerland with for renewal of rails. Then we had a big span to the how to increase safety in the rail freight transport. Then we had information on ERTMS, and finally we came back to the track again and look about possible opportunities in the future to increase service life of a track. So I give all the people in the audience the floor to ask some questions to our speakers. Let's start. So you're all happy with the presentations? Very good, very good. I think it was a long day already. So if there's no question, then thank you once again for this third session. And I would hand over and give our president, Mr. Olaf Scholz-Globloch, once again to make a short finish of the session. And thank you for coming.
Does it work? Hello? Hello? Yeah, okay. Yeah, so thank you for coming here. I like to make it quick, but at first I will say thank you to everybody here in the audience and in the room, and everybody who was participating in which form ever. on this convention. I think we have the possibility at the evening to continue our conversation and also tomorrow. So I will not make so long words to you, but at first I like to please some people to come to the stage because at first I like to honor one of our presidium members, and then I like to say thank you to some special people. So, 1 second. I'm pleased to come, of course, Mario Galabo. Yashin Isher, I hope I pronounce it right. Sorry for doing it not perfectly, maybe. Palina Mladanova. Antonetta Georgieva. Oops. Pauline, haben wir schon? Niklas Schemer. Ah ja. Daniel Wirth. Charlotte Gebhardt. And Hermann Schmittendorf. Mario, where are you? Aha, okay. So at first we like to say thank you to you, Mario, because you were the person who did the most work in order from us. Oh, this is, 1 second, Daniel. So at first we like to say thank you to you, and you have will receive a small present from our group.
Thank you so much.
And additional a certificate, because it's a honor certificate for your long work in the Presidium of UEEIV as member of the Presidium.
Thank you.
Thank you.
I want to say thank you, but thank you for all team of UFO of our Presidium. Thank you very much, Mr. Gomberg.
So we were not involved in all the processes. So these people who stand here from the local team, they are representatives. For sure, you have had some other people behind you, helping you. So many helping hands. Also, thank you to the translators and to the technical staff. And therefore, thank you to you, Mr. Schimmer, no? Niklas Schimmer from Getzner. They sponsored the technical equipment here in the room. And so thank you for this to you. And of course, our Charlotte, she's the secretary in our association, and we have a long relationship now to you. Thank you for everything which you have done for us in the time, and sometimes it's very stressy for you, but every time you are calm and quiet, and everything works well. Thank you very much. And then we have a gift for you. This is a special edition of our editor, Hermann Schmittendorf. He is producing several railway reviews or reviews with the content of railways. And especially for this convention, he was producing this review, which is written in English and also Bulgarian. You are all invited to take an exemplar with you. They are outside behind the door on the right side. Yeah, and Daniel is the colleague who does the most work together with me. He's always available when I call him, and yeah, thank you also to you, and also to all the other members which are not at the stage now. For example, Bernhard, he is a very good colleague of us. He was managing the last session. And I don't know all the names of all other people, but thank you to everybody, thank you to you, and thank you to everybody. It was a pleasure.